Hello, everyone. I'm Ramya. I work as an NLP engineer at chillwall.ai. And chillwall.ai is a startup that specializes in event recommendation. So, we have a very interesting topic today. It's web scale systems, development of web scale systems for scientific knowledge exploration. I'm sorry. So, before I move into the discussion of the paper, I would like to talk about scientific knowledge exploration, and that is for people probably who are not aware of this. I know most of us have done this in our lives, search for relevant scientific material and publications on the internet, something pertaining to the work that we are doing. So, scientific knowledge exploration, if you have to explain it to a layman, it's just that you search for relevant scientific material on the web. And in the age of internet, we have more expectations from such a system. We want it to be fast. We want it to be efficient. We want the results to exactly reflect what we want. So we are going to discuss about a paper which claims to have two contributions. And the most important contributions of this paper is that they have come up with something efficient, the efficient way of exploring the web scale scientific knowledge. And the second thing that they say is that it's efficient because it organizes all the scientific publications into a hierarchical concept structure. So it makes it very efficient for us to explore. So that those are the two key contributions of this paper. So when it comes to the three essential requirements, whenever we are building a system, we give it a requirement specification. So there are three requirement specifications, so to speak, that authors have come up with. First, we identify the concepts, a set of exhaustive concepts that could, that could cover all the publications that have come to date. The second requirement is that we associate these concepts with relevant publication. And the third requirement is that we build a hierarchical system. Of course, I've mentioned 6 level, but it could be any level relevant hierarchy, which organizes these concepts into a very relevant set of, a relevant hierarchy of concepts. Yeah. So, oh, I'm sorry. Yeah, so I was in so the third requirement is that we come up with a relevant hierarchical structure where we organize the concepts meaningfully. And in this paper, of course, during our discussion, we'll be talking about all these steps. And they have developed specific algorithms to implement each of the step. So of course, they also say that, they claim that in the paper that after going through this process, they were able to come up with the most comprehensive cross-domain scientific concept ontology with more than 200,000 concepts and over 1 million relationships. So there are three challenges associated with this entire, that process of building the system, the web scale system. First is in terms of scalability. So the earlier approaches, people used to manually label documents. So that was not a very efficient way of doing it because it was not able to cover, all the million documents or all the million publications that were there. So when you have probably experienced this, that if you manually curate or label something, it's very limited, as in it's not sufficient, it's insufficient, it's inefficient way of doing stuff. So we need something which could do things in an automated fashion and could include all the publications. The second thing was the problem of trustworthy representation. Now, what does that mean? So we have been using, concept extraction techniques And there's so many concept extraction techniques, LDA, YTerm, and all those things. And we have used it on, unstructured data. But the concepts that we come up with, and all of us have seen this, is that the concepts are of they are of subpar quality. I'm sorry, and also they are, they are very restrictive. They lack authority. So, for example, the topics that you come up with, when you're using an algorithm like LDA, can you compare it with a more authoritative concept like machine learning? Or can you exactly, give it a name? No, most of the times you're not able to give it a name. So it's not authoritative. It's not. It's of it's of a subpar quality. That's what. And the third limitation is that there is a temporal element. So, like, it's not that, publications are just created and, new publications don't come in. So every day, 70,000 publications come in. So it's not just, the scale of the already existing publications, but it's like the scale of data that comes in. So there's a temporal dynamics involved. So we have to build a system that takes care of the scale, that the temporal dynamics, and also it takes care of, representing the data, giving a more trustworthy representation of data. And that's what that's what the authors have come up with in this paper. So there are three essential steps that they have defined. First one, concept discovery. You discover the exhaustive list of concepts. The second step is concept document tagging. Associate a concept with the relevant publications. And the last step is, building the concept hierarchy or concept hierarchy generation. So you organize the concepts into a relevant hierarchy. And the end result of this paper was MAG, Microsoft Academic Graph. So, and if you look at the website where they have, the website totally dedicated, and I'll be showing the slide where I have, taken a snapshot of it. They say that this Microsoft Academic Graph powers their Cortana application, Bing, Word, and Microsoft Academic, which is their proprietary search engine tool. So, of course, MAG, there are a lot of, things that they have talked about. So Microsoft Academic Graph, of course, it's meant for semantic search experience in the academic domain. And it's a heterogeneous graph because you see the nodes in this particular graph, they're not of the same type. So it's a heterogeneous graph and it consists of 6 types of entities. One is the publication, author, institution, journal, conference, and field of study. And as of March 2018, if you look at the site, it says that as of March 2018, it contains 170 million publications with over 1 billion paper citation relationships. And it is by far the largest publicly available academic data set to date. So this is the snapshot that I was talking about. So if you look at this, the top left, you'll see that it powers the graph powers Bing, Cortana, Word, and Microsoft Academic. And this is how, if you look at the bottom snapshot, that shows a snapshot of the Microsoft Academic search tool that I was talking about. Yeah. So I would like to, so one thing that comes to our mind is that, oh, well, we have Google Scholar. Why do I have to use Microsoft Academic? And that's exactly why I put this slide, and I'm going to compare the two. Okay, so let's say that I'm searching for a specific topic. Let's say I'm searching for VGGNet. Okay, something for the computer vision people actually. Okay. So if you look at this, the results that have come, it doesn't look that impressive, but I will tell you what's different here. So, okay, let's go to Google Scholar first. It's like VGG net. Okay. So you see that, okay, it has displayed all the relevant, publications, and you can see that it talks about the citations, and it talks about the related articles, and all the relevant versions associated with the same publication. Very good. Okay. So let's go back to Microsoft Academic. So, right, we have seen, we are able to see again the relevant publications here. But what is different here? So if I click on this, I, of course, it's a fairly recent paper, so I have references and citations. For this, it is zero. It's okay because it's a fairly new paper. But then the thing that you have to notice is that it is listing out immediately the concepts that are present inside this paper, like stream processing, shaker, petroleum engineering, and geology. And if you press into this, the individual, you can say, topic, it gives you information about the parent topics. That is the superset that holds this topic, like distributed computing or real-time computing and parallel computing. And then the child topics, probably a part of it, event stream processing, a very specific type of event processing. And one more very interesting thing about this is that it's giving a definition of stream processing, and it takes it from Wikipedia. And 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 I would like to say this is that the basic knowledge base that powers this is Wikipedia. And that's why it's able to directly take the information from Wikipedia and display it in front of you. And another statistics that you get is regarding the number of publications and citations added for the relevant topic. And you also get the total number of papers that might have this particular topic, and then the authors who have worked on it, the citations associated with those papers. So there you go. It has more information, more statistics.
Yeah, just questions. You said uh, uh, a topic. Is it the concept related to
Yes.
concept?
Yes. So what they're trying to do is that every publication, they're trying to see what topics it could be associated with. For example, thermodynamics or physics or machine learning. So that's the topic. Yes, yes, yes. So um, so so this is where it is different from um, Google Scholar, right? So now let's go into the details of each step, how each step was implemented by the people. So the first step is concept discovery. So um, for this, what they have done is that, like in this particular step, they have defined. If you want to understand it, the basically what they've done is that they have a knowledge graph, and inside the knowledge graph, they have different entities. And what they've tried to identify is those entities that could be defined as an FOS type, the field of study type entities, which they have, in turn interpreted as the concepts. So that's the basic thing that they're doing here. Okay, basic crux of it. So, so what they've done is the knowledge base that I was talking about. It's nothing but arrangement of different entities into whatever structure that you want. But you link different entities. Of course, here they have used a graph structure. So they have linked these entities in an is-a relationship. For example, Barack Obama was a president, US president. So Barack Obama, US president. And then you have Tiger Woods and sports person. So you start associating, the entity Tiger Woods with sports person. So, so that's what they've done. So they have created their own knowledge base using Wikipedia data. So here the Wikipedia articles that you have, each Wikipedia article is a concept. So, so that's, they call it as the Wikipedia entity, and the end result was that um, with the help of 5 million such entities in the knowledge base, they were able to extract 228,000 concepts or topics. So, yeah, so when it comes to different levels of hierarchy, what we are actually talking about is moving from a very generalized, topics to more specific topics, right? That's how we logically arrange something in hierarchy. So for the L0 and L1, the first and the second level, they wanted to define very generalized topics. So they didn't particularly use the knowledge base that I was talking about. So these concepts, they were extracted from existing taxonomies. So one such existing taxonomy that they've used and they have cited in the paper is the science metrics um, metrics classification. So this is a pre-existing taxonomy that researchers came up with, and I'm proud to say that this was, a brainchild of a scientist, the University of Montreal. So uh, a person from Canada has come up with an English version of the classification, the hierarchy. So they have come up with a 3-level classification, and from this, the authors of this paper have extracted the concepts belonging to the L1 and the L0 level. I mean the L0 and the L1 level. So, so there are 19 topics that they've extracted, generalized topics that would be like, physics, chemistry, mathematics, and all. And the L1 level, if you look at it, it consists of machine learning, which is a part of, computer science. And then you have microbiology, which is a part of biochemistry, biology, and all that stuff. So this is how they have come up with more generalized topics for the L0 and L1 level. For the L2, all the other levels, L2, L3, L4, L5, they have come up with the topics they've extracted from the knowledge base. And how have they done that? Essentially, they've used 3 steps. One is the initialization step. So what they did was they identified 2,000 high quality, entities in that knowledge base, which they classified as field of study. They initialized it. It's like an initial seed. And then they proceeded to move to the 2 steps, which is the graph link analysis and the entity type based filtering. So in the graph based analysis, what they have done is, selected a particular entity and they have calculated the n nearest neighbors. And the algorithm that they have used, of course, they've calculated the semantic closeness. So for doing that, they have used a measure which is called as Wikipedia link-based measure. So there's a paper totally dedicated and for this, measure, and I encourage people to look at it because it's very interesting. So to at a very broad level, what they've done is that use the hyperlinks in different Wikipedia articles to calculate the semantic closeness. So hyperlinks, in a Wikipedia article, it takes you from one article to another. So their assumption is that if the type of hyperlinks present in a particular article is similar to another hyperlinks present in another article, then they're semantically close. So they've used that measure to calculate the closeness. And here in this paper, they have used, I'm sorry, they have used the WLM measure to calculate the n neighbors. And let's say the n neighbors there are 100 n neighbors that they come up with, nearest neighbors. So they see the entity type of each of those neighbors. And if let's say k out of n, k are of the field of study type, and if that k is above a threshold, which they say is in the range of 35 to 45, then the entity type, they say that that particular entity is a candidate for field of study. So, so that's what they've used, and that's the graph link analysis step. But then they don't stop there. They go to the next step where they do some sort of enrichment and filtering. So they look at that type, the entity type, and they have used the freebase dump database, which is nothing but it's just a dump of all the sentences where they have extracted the subject, the predicate, and the object in the sentence. And that's how they have intuitively tried to figure out, indirectly tried to figure out the entity type for a particular entity that they have found out in the graph. So, that's sort of a ground truth for them. And what is that? So they're using this particular thing to filter the candidates. So let's say that they've identified a certain entity as a field of study, as a candidate for field of study type. Then they indirectly use this freebase database to get an entity type for that particular node. And then if it's acceptable, if you think that the entity type is acceptable, then they take it as a field of study, or else they just discard it. So to give you a small example of this, let's say that while using the freebase database, they come to know that that entity is a person. Then it's most probably the researcher, right? So a researcher cannot be a field of study. So let's say if that particular entity, they come to know that it's a type of amino acid or it's a protein, then yes, it's most likely a field of study, because people study about proteins. They don't study about researchers, but they study about proteins and amino acids. So that's how they filtered it out. And yeah, the next step, of course, is linking the document with concepts. So before I move into this, there's a small thing that I would like to mention, that they've essentially, for doing this concept document tagging, they have used textual information and the graph structure information. One more thing, again, in this step, the basic crux of what they've done here is that they have defined a vector for your concept and vector for your document, and calculated the semantic closeness using a measure like cosine similarity. And if the result of that is above a certain threshold, then they've said that, okay, we can tag this document, this publication, with the concept. That's the basic thing that they've done. So what's interesting is how did they come up with a vector for a concept and a vector that could describe the publication. So as I was telling you, they've used two pieces of information. One is the textual and textual information and the graph structure information. So when it comes to the textual information, for the concept, which is a Wikipedia article, they have used the first paragraph of the Wikipedia article. And for the publication, they have used the meta information associated with the publication, which is the title, the keywords, and the abstract. So that's the information that they've used for the publication, basically. So one thing that I would like to say is that when you're talking about vectors, in the NLP state, it's just that the text gets converted into vectors. So that's why I'm talking about the text that they have used essentially. And the graph structure information is just that they have identified certain neighbors for the publication, using the citations, using the references, and using that information, and also the venue, the publishing venue, and all the textual information pertaining to the publication venue, the citations, the papers that have been cited, or the references, all that has been used for a certain publication. And when they have used that, they claim that they've used the graph structure information by doing that. So So the text has been represented into two different types. One is the simple representation of text, or SRT. So in simple representation of text, I told you for publication venue, they've used the publication venue name. For the Wikipedia article, the first paragraph of the concept. And then for the publication, they have used the metadata. For the extended representation of text, which is the graphical structure that they have used, they have, for the venue, the set of all the publications that were produced in this particular venue, their SRTs have been concatenated or aggregated. And then Wikipedia article, of course, for the broad disciplines, let's say, you have something like a topic like machine learning. And if you go into the Wikipedia article that describes machine learning, it's very vague. So for that, what they have done is they have associated concepts with publishing venues, and they have made these concept venue pairs. And for the venue, the extended information for the venue, that they aggregated it for the concept and came up with the ERT for the concept. And then for the publication, they have used the simple representation of text for all the citations, the references, and publishing venues, and they have, included that as the extended representation text. So the thing is that you are not only using the text which is there in the publication, but you're also using the extended version, as in, the text which is present in the citations and the references. So this is the formula. Of course, it doesn't look that intimidating. But then one thing that I would like to highlight here is that when they were aggregating, they used something like here W sub I. So the W sub I, W sub J that you see here is basically a discounting factor that they have used. And in the paper, they say that all these weights were determined empirically. They don't reveal the actual algorithm or the function that they've used for the W's, but they say that it's a discounting factor, and it has been used, it has been determined empirically. Okay, so.
Can I ask a question?
Yeah, sure.
I'm kind of lost. Can you explain what HEF, what H is?
Oh, yes. So H is, I'm sorry, thank you for asking this. So H is the vector representation that I will be talking about. So, you will be, like, that's the next step. I'll tell you what H is. So they've simply not used, usually when we talk about NLP, what we do is that we use just one feature, probably embedding of words or bag of words model, right? But they have used 4 different features. So that would be bag of words, bag of entities that they've extracted from the name of the entity, embedding of words, and embedding of entities. So they've used these 4 features, and they've extracted the feature, extracted the vectorial representation, so to speak, and that is your H. And the word embeddings, they have not used the word embeddings like, the ones that are already available, like word2vec or something. They have pre-trained the word embeddings by using skipgram on academic corpus with 13 billion words based on 130 million titles and 80 million abstracts. Of course, they've developed vectors which are of 250 dimensions for 2 million words and phrases. I'm just reading it verbatim from the slide, but I can't keep this in mind. But then it's a vector of 250 dimensions. I mean, a dimension equal to 250, and that's how they came up with these embedding of words and entities. So as I told you, there were 50 billion pairs, and out of that, they were able to come up with 1 billion pairs, using the confidence score that I was talking about, the cosine similarity between the vector representation of the concept and the publication. So we are in the final step, which is, oh, sigh of relief for all of us. So concept hierarchy building. So basically they have used a principle which is called as the subsumption principle. So let's say there are two concepts, X and Y, and Y is present in a set of documents, subset of documents in which X is present. Then they say that Y is the child of X. So to give you a sense of this, let's say there's a topic like permeability. Sorry, I'm taking your example, Karim. So there's a concept like permeability, and let's say it's found in all the publications of, let's say, um, physics. We're talking about electromagnetic permeability. So it's present in according to the subsumption model, since permeability is present in all the publications which are associated with physics, permeability becomes the child of physics, right? But this is not actually true, because permeability could be it could be related to physics, but there's one more permeability if you're aware of biology, permeability of membranes, right? So it could also belong to biology, right? So it means that Y could be present in the subset of articles of X1, X2. So you can't really strictly use this subsumption model. So they have come up with a more intuitive measure, which is called as the weighted relative coverage score. So let's say that you have I and J concepts, and the set of articles that contain the concept I, we represent it with capital I, and the set of documents that contain the topic J, we call it as like, we represent it with capital J. And then we have yet another type of concepts, intersection J, like they're the set of documents that contain both the topics I and J. I'll call it as, you know, the intersection set in my explanation. So, and then you have W sub ik, which is basically the confidence score that they have calculated in the previous step. So it is simply the confidence score of the concept I and the document K. So if you look at this intuitively, the left-hand side term, the term on the left-hand side, I'm sorry, that represents the semantic closeness of the documents in the intersection set that I was talking about and the topic I. And let's say that the term on the right hand side, I'm sorry if I'm messing up the order. So this is the one that is close to I, and this is the I and I'm sorry, it's basically the representing the semantic closeness of the documents in the intersection and the concept I, and this term it represents the semantic closeness of the documents in the intersection and the topic J. So if you intuitively see this, let's say that if the term on this side, if it's greater than this, what does it indicate? It indicates that that the topics in the intersection are closer to the topic I than J. So whenever you have a child topic and a parent topic, you know that the parent would have so many different children, right? So it's intuitive for the documents to be closer to the child topic than to the more generalized parent topic, right? So it means that basically it's a child of J, right? So that's what they've used. They said that if it's positive, if RC is positive, it means that concept I is the child of J. So using that, They have been.
Kind of. I was wondering about the main formula there. So there's on the others on the top of the division. Um, on one side of the intersection operator, there's all of the documents tagged to I, but then on the other side, what is the J that's multiplying WI sub IK?
Okay, so you have two concepts, I and J. If I've understood your question correctly, you're asking me what is a W sub I as a W sub JK on the top.
How is J multiplying with that? Like what is J?
So so it's, I'm sorry, because of the sheer size, I think it's getting multiplied, but it's not getting multiplied. It's the sigma summation k run. I mean, it's just summation on the k documents, and k belongs to the intersection ij. There's no multiplication taking place.
It's just that okay.
I'm sorry. I should have reduced the size of this. Mm. Yes, yes, I agree. I'm sorry. So,
So to be clear, I think you're just summing up those confidence scores.
yes,
Um,
yes, precisely.
according to like whatever subs there is. I think you're summing over K over
Yes.
there, and J would be constant.
Precisely, precisely. So this is just a summation of the confidence score, as Ehsan described. It's just a summation. There's no multiplication going on. It's just a sum. Are you clear? So, so at the end, they were able to come up with, you know, uh, yeah, like I said, they came up with 1 million parent, yeah, parent child. Just this slide. It's last slide, and then we can.
Then let's take a break.
Okay.
Let's take a break, and then we come back to this.
Yeah, and yeah, sure.
Unfortunately, the results.
So, so we were discussing about the last step, that was, building the hierarchy. So they used the weighted relative coverage score to determine if, a certain topic I was a child of the topic J. And they have come up with 1 million parent child pairs. So another thing that they mention is that for the L0 and L1 levels, since the topics are, they have high impact, high visibility, and they're of small size, they have manually created the hierarchies because they wanted to be absolutely sure about the child and parent relationships that they are creating. For example, computer science is the parent and machine learning is the child. So I'm just giving you an example of the type of parent and child relationships they created, but that was done manually. But let's for the other concepts in the L2, L3, L4, and L5 levels, they have used this automated process that I was talking about. They calculated the RCs to determine the parent and the child relationships. And this snapshot, it shows a sample, you can say, series of parent and child relationship that they have come up with. For example, computer science, machine learning, artificial neural networks, deep learning, deep belief network, and finally, the more specialized one, convolutional deep belief networks. So that's just one example. And the two drawbacks that they have cited for this step is, are, first of all, intransitivity of parent-child relationship. So briefly, if you have to describe transitive property, it's just that if you have A is related to B and B is related to C, then we could infer that A is related to C. That's a transitive relationship. But what they've said is that the kind of hierarchy that they have built, it does not allow such transitivity to exist. So it's intransitive. The second thing is that there is lack of type consistency check when they come up with the parent-child relationship. I could give you an example. For example, and this is one example that they have given in their paper, and that's, let's say you have the polycystic kidney disease, right? So you would find the concept of polycystic kidney disease in all the papers associated with the kidney, basically. So kidney is an organ, right? But the child of kidney is polycystic. According to this algorithm, it's polycystic disease, kidney disease. So how can a disease be a child of an organ? So that type inconsistency comes in. So those are the two limitations of the step.
Can you explain again why they have to just manually adjust between L0 and L1?
So they were more generalized, and they thought that it's something that would be highly visible to the people, right? So they wanted to make sure that these hierarchies, that's what they have mentioned. They are high impact. They are limited, so they could do that manually, right? Because there's just 19 concepts in L0 and 294.
So, that's what they mean by impact. Okay, I see.
So if you have, so the impact, I think, means if you have an error in one of those two layers, then it will propagate throughout your entire hierarchy.
Yes. So that's why they thought that they could, make do with, just doing it manually. So finally, I would like to explain the evaluation process. Although they have not given the accuracy scores, but they have just described the process, how they evaluated the outcomes of their different steps. So each of their steps, it was evaluated separately. So for the concept, what they did was they selected 500 data points for each step, and they used human judges to say that whether it was good or it was not good. For example, let's say for the concept discovery, the data point was a field of study. So they had just asked human judges if it was a field of study, like whatever they came up with was really a field of study or not. So if their answer was yes, then the label was positive. Otherwise, it was a negative. The label was negative. And similarly for the concept document tagging, whether the concept publication was really, it was a right pair, it made sense or not. And for concept hierarchy building, again, whether the parent-child relationship that they came up with was really meaningful or not. So that's how they evaluated the 3 steps and used human judges, asked them basically. So 500 data points, again, subdivided into 100 data points, and each group given to one person to evaluate. And the accuracy was simply the proportion of positive labels in that particular group. And you had 5 groups, so they just averaged the accuracy score. So that's how they evaluated. And one more thing, of course, one extra thing that they have added in this evaluation process is that the third step, they said that it's a little subjective when we're evaluating a child and a parent pair. So for each of that 100 group, instead of 1 human judge, they had 3 human judges for each group. So that's the only difference. Otherwise, this is the measure that they have come up with, the accuracy score. And unfortunately, they have not provided the accuracy. I don't know why. In the paper, it was not provided, but the process was explained. So now we come to the interesting part, discussion points. And these are the essential things that I wanted to hear people's ideas about this. The first discussion point is the intransitiveness that I was talking about earlier. So do all of you feel that it's a limitation? You think that, let's say if a relationship is intransitive, let's say if I have A is related to B, B is related to C, and I cannot link, but I cannot say for sure that A is associated with C. Is it particularly a limitation?
It makes sense. That's a limitation. Because I mean, if you think about it, a bird is an animal and a dog is an animal. So you can go, okay, there's a link from bird to animal to dog. But the obviously.
Sorry, do you want to talk a little bit closer to the mic?
Oh.
So we can capture it. Thank you.
Sorry, I was just going to say that it makes sense as a limitation because a bird is an animal and a dog is an animal. So you can think of that tree like bird, animal, dog. So it makes sense that it's not that the information doesn't flow any which way there, because yes, dog and bird are both children of animal, but they're not related to each other. And if information flow was transitive, then you'd think that there was more of a relation between the children of parent nodes.
Yes.
So there should be some limitation on how the transitivity is going to work, right?
Yes. So, the question was whether you think it's a limitation or not. How is it a limitation? Like, if I have like he was saying, if there is it's something a bird, and another thing is also associated with bird, then both are like birds essentially. But then if that relationship does not exist, is it like a limitation? How is it a limitation?
Just to have some context, in the paper itself, they say it's a limitation. And that's why this is a discussion point.
What's their reason?
That's what, because when, Karim and I, we were discussing about that yesterday. So when we were discussing about this, we were just scratching our head. How could this be? Is it really a limitation? Of course, they mentioned that it's a limitation, and we cannot. It's not like blind faith that we can go with whatever they say, right?
So I think to counter that, so if you're talking about easy relationship, Porsche is a car, a car is a vehicle, so Porsche is a vehicle.
Yeah.
Right. So that transitivity does exist, and if you have a tree, perhaps you should be able to infer that. So I'm not sure if they're saying that. So are they saying that okay, that transitivity exists? Now maybe we can evaluate that and see if that works or how well we're doing it, because they already are creating the tree, so it should be there. Or are they saying that we should have that from some knowledge base and inject it in our algorithm and see if it does better? So those are my different points of views.
And just to add on that, it might be that the algorithm that they use to find parent-child relationship does not work for two steps away from the child. So the parent of the parent will not be detected as a direct parent of the child in their algorithm. It might be that they were referring to that point.
Yeah, I mean that's a limitation. Yes, I think that would certainly be a limitation, right? When let's say that A is the child of B, and B is the child of C, then we should be able to infer that A is the child of C. And if you're not able to do that, then that's a limitation. And even when we're trying to traverse the graph, I mean traverse some sort of a hierarchy, tree structure, if I'm not able to move, across levels, different levels, that's certainly it's a drawback. So I think Karim is right. If you're not able to do that, and the transitivity does not exist, then there's a problem. Yes. And one more thing that I would like to add is that I felt that it's also because a child could have multiple parents, and that becomes an ambiguous relationship. For example, thermodynamics, like I was telling you, it could be associated with physics. It could also be associated with chemistry. And if a person is just saying, tell me about publications in thermodynamics. So what are you referring to? Are you referring to the physics side of it or the chemistry side of it? So that becomes a limitation. So it could be that, one interpretation could be what Karim gave, and also Ehsan, and one interpretation could be what I said, probably, multiple parents and one child. Yeah. You want to add something? Yeah.
I was just thinking about that before because I imagined intransitiveness as having a different meaning than what you said it, but just now. So were you implying that or saying that in this net which it creates, that there is no way of traversing from a child to the parent?
Yeah, when you have multiple parents, then which way would you go?
Oh, so but there is a link between children and parents.
Yes, there is a link.
Okay, because I was gonna say if you don't have that link, then do you really have a graph? But there is that.
No, we do have that link, but
So, yeah.
the problem is it's ambiguous, which way to move. That's it.
Okay, so that was a great question, and I think like we may have been able to set it up a little bit more visibly. So you're saying because when you talked about the scoring, you did mention that you compare the parents and then you score them. I think the original assumption, like the immediate assumption, would be okay. Then there is only one parent, right? Because that could be the highest score, and it's less likely to get equal scores per child per child. But what you're saying is that beyond above a threshold, perhaps we count those as parents.
Exactly.
Therefore, you have ambiguity now.
Yes.
So that there you have a transitivity issue.
Exactly.
So you don't know which. Is it actually both of them? But still, I think that can be verified. I can't come up with an example that says, I don't know.
It's just a constraint satisfaction.
Yes. Yeah. And I think he's right. Ehsan is right. Instead of just looking at a positive threshold, why can't you could just possibly rank those scores, which would give you a better understanding of parent-child relationship. And it would remove that ambiguity. It's better to have ranking because it makes no sense. If you just set a positive threshold, there could be multiple parents for the same child. But then if you have a ranking system, you would know which one is. It's like a super parent, and you have a parent and direct immediate parent and all that stuff. So ranking would certainly take care of this. Now the second thing that we were really which was like hair splitting was they said that it's computationally prohibitive to compute weights. So they have do you remember the discounting factor that I was talking about? So they've said that they have determined this discounting factor empirically. So I wanted to hear if people, if they have used some strategy to determine the weights in their algorithms or in their research work. So I just wanted to hear what could they possibly use? How could they, empirically determine this weight?
Sampling.
Could you elaborate on that?
That they could just, given that the graph is huge and it's computationally expensive, if they have n connected nodes, they just take a subset of them, just randomly sample, compute it for that, and then for that small sample while they iterate over the nodes in there, so that they're not, so it's not exploding.
Interesting.
Can you go back to the slide that has the formula?
Oh, sure.
Yeah.
So I was referring to these weights, and they said that they determined it empirically.
Which weights exactly?
W sub I for the citations. So they didn't directly aggregate the SRTs. They used a discounting factor, W sub I, for the citations, and W sub J for the references. It's just that they have used discounting factors. while taking into consideration the ERTs of different papers.
Can you remind me what C sub U is again?
Which one?
What is a C sub U? The first sum and the
This one?
subscript of the first summation.
Oh, the first sum. Okay. So these are basically the SRTs of all the publications that were cited in this publication. So it's the sum of those SRTs, but they have used a weight, used a discounting factor. But that weight, they have said that they have determined it empirically. So I was interested in if people have, in their research, if they have used some function, how to determine this W. It's very interesting, right?
So they're discounting the citations of a search paper.
Yes.
Oh,
yes.
maybe they're just like, could they be going by the impact factor of the publication, maybe? Weight those less?
Could you elaborate on that?
Well, certain journals are either regarded higher or lower. They're associated with a certain score. Impact factors, the jargon. So like Science and Nature are really highly regarded, whereas other journals aren't. So
that's interesting.
Weight Nature and Science greater than some of the subpar journals.
But in that case, shouldn't the index be on the venues, but instead of the individual citations?
Mm-hmm. Oh, I was thinking, is it related to how correlated the citation was to that publication? In terms of how related it was, because you have several papers that cite certain things, but then how related was it to the actual topic? Let's say that I am, for example, talking about some cutting edge, a state-of-the-art algorithm that's related to, let's say, neural networks, and text generation, for example. And then I'm citing at a very small place. I'm just citing probably. I've used, of course, word embedding. So I cite a very small portion. I just cited somewhere that I've used this word embeddings, and I cite the associated paper. So it's not very impactful when it comes to the actual paper, right? It's not very correlated with the actual work of the paper. So is it that particular weight they're talking about, how correlated it is to the actual topic?
I mean, we can only speculate because they said we use it empirically. They
Yeah.
might be using impact factors along with similarity, along with many other factors to determine their weights. So, and to answer your question, so like every publication is in a venue, so they can still use the venue's impact factor.
Okay.
So they can also include it somehow, if that was part of their empirical formula.
So in other words, not all citations are created equal. And then,
Some are more equal than others.
I was also reminded of Karim's example. Like he was telling me that when he was writing his paper, the person who was looking at his paper said that I would only pass it if you add these citations. So of course Karim would have felt at that moment, what is he talking about? It's not even related to my work. But the researcher was old and he had to appease the person, so he had to just add him. No, just kidding. So
I can think of some.
well, it has happened to me, Karim. So I'll say it bravely. I had to add some 4 or 5 citations. So I'll say that.
It's happened to everyone.
Everyone, you have to add.
So maybe something like, if the citation is on the related papers, then it's highly relevant. But if it's something towards the end of the article, it might be less relevant. But it's a very wrong metric.
You can't say that actually, because I think the way the papers are cited, it's the citations are in the order of how they occur in the paper, right? So it really doesn't make sense if it's at the fag end, it's not important.
But
think you were saying the content or the citation?
Like in certain sections, it might be more relevant. Like say if it's a related work, that section might be relevant. But if you cite it at something end, like the toward the end, like experiment.
No, it could be. It could be the main competitor you compare.
No, that's what I'm saying. You can't say that actually because the order in which it's just the order in which it.
But if it's cited in the abstract, then it's got to be more important.
Actually,
Okay,
maybe
okay,
in the introduction,
You can't say that actually.
if it's in the introduction, it could be just like a topic review. It's not that relevant, but in the main text, it's more relevant.
But I think the general point, which is true here, is that there could be heuristics. Like they can look at those and figure those out statistically. I haven't done the experiments.
And one more thing, it's interesting what you said because let's say that the papers that they cite in the related work, it would be more important than let's say the papers that they cite in the algorithm portion because, like I said, like let's say that I'm just using word to work in a certain step, and it's not actually related to what work I have done. I've done some ground-breaking work in, let's say, the type of architecture that I have designed. But just one step that I have for that I've cited the paper related to what to work. It's not very important. But then again, it depends. Yeah, it's scenario-based. Yes.
Yeah, I actually think that probably makes sense. Some similarity score, because I've done the same thing, written a paper and then just done the obligatory reference to like some math equation that I used that wasn't really relevant. So if there's, I just had to. Yeah, exactly. So if they had some, heuristic to see how similar they were, they might use that. That's a good idea.
Yeah. Any more thoughts?
I actually just have an unrelated question about how I guess they didn't go into too much about the accuracy, but they picked 100 people to do this manually. Like, wouldn't you want domain experts to like rank, especially when you get into like the real subtopics? Like, unless you're an expert in the field, you'll have no idea if these are good or bad hierarchies of topics.
Yeah, you're right. You're right. Yeah. Because one thing that I would like to say is that how could they say that machine learning is just a subtopic of computer science? Like you can't say that it's a child of computer science only, because if you have all, like we have all worked in this field and we know that it could just not be the child of computer science, right?
But they allow multiple parents, right? So they only showed one example, but it could be that machine learning is under several parents on their websites. I mean,
but for that's what I said, for our L1 and L0, they've done that using their own measures, right? So that's what, it's very subjective, right? And he's right, like you cannot rely on the opinion of any random person, like who are those human judgment? It's like you have to be very specific, as in who was that human, like it's just 2 paragraphs where they've talked about the evaluation process.
Did they talk about who the annotators were?
No, okay. That's what.
So the other thing that's also wrong is that, not wrong, but like maybe could have done in a more elaborate manner, exactly, is the inter-annotator agreements, because if there is some agreement, but like half of the time they're disagreeing, then what the hell, right? And if you want to be more strict, then you have a kappa agreement, which separates agreements by chance from your computation of the agreement.
Correct. Yeah.
So if more comprehensive version of the paper could include those.
Yes, you're right. And one more thing is that they just, for the accuracy score, they're just taking the average. So they're not talking about the variability as he cited, they don't check for the variability. Maybe you could have a person who is like very, very lenient and he says, oh, everything is good. And there's like one person who's like very strict and he's like, I don't like this, I don't like that. And then he's like giving a very bad score. You would not come to know because, it just averages out. That's it. So, it's a very simple heuristic. They've not given who those human judges were. And then very simple averaging.
I did though look at my I looked up myself on the thing, and the tags were very accurate on my publications for the most part. So I did a good job. Except one of my papers was titled "Accounting for," and it was tagged with accounting, even though it's a niche physics subject. So everything else was good except for that.
So you know accounting is well.
You can change your career.
Yeah.
To jump back to the previous point, something hit me, maybe about it. So a simple other measure perhaps for a citation be more relevant is how many times you cited them. Because like if you're talking about them in the intro, and the review, and the conclusion, results, it could probably, the
More
frequency
related,
could.
yes. That's right. The number of times it has been cited, yes, makes sense. Perfectly.
All right. Thank you so much, Ramya, for a great explanation of this paper. Thank you, Ehsan and Karim, for great discussion points, and thank you everyone for coming here. Our next event is on May 6th, next Monday, and the topic is going to be deep temporal logistic backup features. So if you are a first comer, make it a second. All right. See you all on Monday. Thank you, everyone.